In this video, we are going to discuss about Newton's formula for velocity of sound and Laplace correction. Okay. So before we start, please subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. So if you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. This is my Insta ID. You can follow me on Insta. So now let's start. So according to Newton's formula, the velocity of sound in a gas is given by the formula V is equal to B by rho. Okay, is V is equal to B by rho. So this is the velocity of sound in a gas. So now you see here the this B represents bulk modulus of elasticity. I'm gonna show you how to derive this equation, okay, of the gas, bulk modulus of elasticity of the gas, right? And rho is the density of the gas, and rho is the density of the gas, right? So now you see, so this formula that was which was given by Newton, he considered that the process of propagation of sound wave through a gas, let me write here I will explain the reason why I have written here I. According to him, according to Newton, the process of propagation of sound through through a gas is isothermal. Okay, so that's why first let me write this. As sound wave travels through a gas medium, through a gas in the form of compressions and rarefactions and Newton assumed that the change in pressure due to compression and rarefaction, there will be change in pressure in the gas medium. Okay, the changes in pressure and volume of gas when sound wave are propagated through it are isothermal. So this was the Newton's assumption. Okay, so if this is an isothermal process, first let me take this as equation number 1, right? If this is isothermal process, now let me take a new slide, okay, to explain this. So for a certain mass of gas, for a certain for a certain mass of gas. If we consider the initial pressure, under isothermal condition, we know the gas equation, under isothermal condition, we know that PV is equal to constant. PV equal to constant, right, for isothermal process, where P is the initial pressure and V is the volume, right? V is the initial volume of the gas, right? So now you see, if we differentiate both sides, okay, so if we differentiate this, so here we have to consider two functions. This is first function, second function. If we apply the product rule, differentiating both sides, what we're gonna have? We're gonna have first function derivative of the second function, that is dv, plus second function derivative of the first function, that is dp, okay, and derivative of constant is 0. That's what we have got. Now this can be written in this form, that is p dv is equal to minus v dp, right? Now from here, what we're gonna have, p is equal to minus dp, we can write dv by v, we can write this, okay. So this is the numerator here, okay, because you see, actually one more step was there, that is p is equal to minus v dp by dv. So this system can be written in this form, right? Hope you have understood this. This is a very simple simplification. So now here you see, according to the definition of bulk modulus, right? If you remember the definition of bulk modulus, here stress is F by A, okay, divided by change in volume by original volume. So F by A is nothing but pressure, here pressure is dp, okay. So that's why we can say this is bulk modulus of the gas, right? This is nothing but bulk modulus of gas in isothermal condition, we can say that way. So if that is the case, now if we use this in equation number 1, if we use this equation number 2 in equation number 1, what was equation number 1? This was the equation number 1. Let me copy this equation number 1. So here is the equation number 1, okay. If we used this equation number 2 in equation number 1, here instead of bi, if we put p, then what we're gonna get? So using 2 in 1, let me write here, using 2 in 1, what we can write, just using 2 in equation number 1, we get here, you see, in this equation number 1, we're going to replace this bi by p, right? So this is what we have got, right? This is what we have got. This was the Newton's formula, for velocity of sound in gas. So this is the Newton's formula for velocity of gas. right? Sorry, velocity of sound wave in a gas, right? So this was the formula that was given by Newton. This is the formula given by Newton. Okay, so if we use this formula to calculate the speed of sound in air, then what we get? Okay, so let's find the error in the Newton's formula. Okay, that was corrected by Laplace. Okay, so now let me copy this last equation that we have got from the Newton's assumption. So that's what we have got. So now error in Newton's formula, let me write this one. Error in Newton's formula So using this formula, if we calculate the speed of sound, velocity of sound in air at NTB, that means normal temperature and pressure. Okay, so let me write this one here. Okay, so now you see velocity of sound in air at NTP, normal temperature and pressure, according to Newton's formula, what we're gonna have? We're gonna have this. Now, how to calculate here pressure? Here you see P is equal to rho g h or h rho g. Here you see this should be equal to 76 into 10 to the power minus 2 meter of Hg Coulomb, right? So this can be calculated this way. So here this is the density of the mercury, and g is the acceleration due to gravity, and h is this 0.6 here. Okay, so 0.6 in 6 means 76 into 10 to the power minus 2, right? That's what we have got. So if we use this value here, okay, then what we're gonna have, root over, let's copy this value of P divided by density of air. So density of air, which is equal to nothing but 1.293 approximately, and using these values we're gonna have 280 meter per second. 280 meter per second. This is the velocity of sound in air, right? So, but we know that velocity of sound in air is approximately 332 meter per second, the experimental value that we used to get. So, which is not equal to this one, right? So that means there is something which must be wrong in his assumption. So what we have conclude from this result, that we can say that this result is different from the experimental value, which is 332 meter per second. which is 332 meter per second. So let me show you the percentage of error. So here you see percentage of error. So first let me write the experimental value minus the value we have obtained divided by the experimental value, which is the correct value, into 100%. That's gonna give you the percentage of error. So which is gonna be approximately equal to 16%. Approximately 16%. So this is a huge error. So this was corrected by Laplace. Okay. So now let us discuss about Laplace correction. Laplace correction. Okay, Laplace correction. So here you see that according to Laplace, Newton's assumption was wrong. Newton's assumption was wrong. Newton's assumption was wrong. Right. So and instead of the process of propagation through the process of propagation of sound wave through the gas, instead of isothermal it should be adiabatic according to Laplace, right? So that means here you see according to Laplace the changes of pressure and volume of gas due to the propagation of sound wave through gas is not isothermal, but adiabatic, right? So therefore what we can say, Newton's used this formula V is equal to BA, that is bulk modulus, BI bulk modulus by pressure. This was for isothermal. So now Laplace used this same formula but here bulk modulus in adiabatic process. So here we're going to use the adiabatic process, bulk modulus of the medium during adiabatic process. Okay, so here using the coefficient of adiabatic elasticity, right? So let me write something here, just wait. So instead of writing only just bulk modulus of elasticity of gas, if we mention that it was considered in adiabatic process, that will be better. So let me write this way: coefficient of elasticity in I should just let me keep it this way. Okay, that's fine, no problem with that. So as we have already mentioned the region here, okay, just wait. Okay, now what we're gonna write, the velocity of sound in gas is V is equal to root over, now instead of bi we're going to use the symbol ba, right? So here let me write within bracket ba by rho, which is the density of the gas. So, and during adiabatic process, you know, under adiabatic condition, under adiabatic condition, p v to the power gamma is equal to constant, right? p v to the power gamma is equal to constant. We know this, and here the gamma is nothing but Cp by Cv, specific heat of gas at constant pressure, divided by specific heat of gas at constant volume. So ratio of two principal specific heats of the gas, right? So now let's differentiate both sides. So let me go back to go to a new slide. Okay, so this was the last equation we have got. Now let us differentiate both sides. Differentiating both sides. So if we differentiate it using the product rule, first function is P, pressure, and second function is gamma, V to the power gamma. If you differentiate this V to the power gamma, we know that ddx of x to the power n is n into x to the power n minus 1. So consider V as x, gamma as n. Then what we should get, gamma V to the power gamma minus n. That's what we're going to have, right? So gamma V to the power gamma minus 1. That's what we're going to have. Then dV, because here we don't know with dV should be written, because here you see we are not differentiating with respect to V here. Okay, here the function is this is the function of x, and we are differentiating with respect to x, but here we haven't mentioned with respect to which variable we have differentiated this. So that's why dV should be written. That means you can consider that way, that you can write this this is n x to the power n minus 1. That means you can write this way, dx to the power n is equal to n x to the power n minus 1 dx, right? You can write this way. So that's this form we have written here. Hope you have understood this. And then plus second function, derivative of the first function, that is dp, then derivative of constant is 0. So that's what we have got, right? So now you see, let's simplify this. If we simplify this, then what we're gonna have, so gamma p v to the power gamma minus 1 dv is equal to minus v to the power gamma dp. That's what we're gonna have, right? So now gamma p is equal to minus v to the power gamma dp divided by v to the power gamma minus 1 dv. That's what we're gonna have, right? So now you see, if you cancel this by this, then what you're gonna have, so this is gamma minus 1, this is gamma. That means you can consider this situation, v to the power 5, v to the power 4, sorry, right? V to the power 4 means 5 minus 1, right? If you cancel this one with this, then you're gonna get v only, right? Same situation is here. So we can write minus v dp by dv, which again can be written this way, that dp, which is change in pressure, by dv by v. dv is the change in volume by original volume here. So this is again bulk modulus, right? So here we're going to write this BA for adiabatic process. So that's why here you can see, so what we have got gamma P is equal to BA. So now let us use this equation. Let me go back to the previous slide. Let me take this as equation number 2 and this is equation number 3. So using 3 in 2. So what we're gonna get, what we're gonna do here, we're gonna replace this BA by gamma P, right? We have got now BA is equal to gamma P, right? So then this B will be equal to the velocity of sound V, that will be equal to gamma P by rho. And if we use this formula to calculate the speed of or velocity of sound in air, what we're gonna get? Now you see root over gamma, you can write this way, right? Let me show this one in the next page. So here is the corrected formula given by Laplace, right? So now you see, using this equation, according to Laplace, or you can say, you can write this way, using Laplace equation, using the corrected formula, right? The velocity of sound in air, that will be V is equal to root over gamma P by rho. So we know that this can be written as root over gamma into root over P by rho. So we have already calculated this, right? This one here, you see here, you can see this is, we have already calculated this. Root over P by rho is equal to here approximately 280. So we're gonna put this value here, we're gonna replace this by 280. So root over gamma into 280 meter per second, and value of root gamma, that is root over 1.41 at okay, for air, for air this value is value of gamma is 1.41. okay, it depends on the type of gas, okay, nature of the gas. So 280 meter per second. So if we calculate this, we're gonna get 332.5 meter per second, which is very close to the experimental value, that is 332 meter per second, right? So that's why this formula is correct. So this value we can write here, we can write this value agrees fairly well with the experimental value. With the experimental value of velocity of sound in air, right? So that was all about Laplace correction and Newton's formula for velocity of sound, right? So thank you for watching. See you in the next video. Stay connected. Bye bye.